All right, let's take this opportunity to introduce the concept of forces, which are kind of the backbone of physics. So we're starting out with some big stuff here. First off, let's describe what a system is. So in physics, a system of objects is simply a collection of two or more objects that are considered together for the purpose of analysis. So these objects can be anything from individual particles to entire planets. It all depends on the situation, right? So if we can see in this picture here, we have two individual objects. We have object A and we have object B. But as we can see, those two objects are connected with this string. And so because they are connected, they are going to move together. They're going to accelerate together. They're going to change their position together, right? So because they move together, we can analyze them as a whole. And so anytime we talk about systems, we just talk about two or more objects that are connected. The key is that the system is a defined grouping, and its behavior is studied as a whole. So like if two or more objects are connected, they're going to move together with the same acceleration, and any forces that are internal to the system can be ignored. And we'll get more on that in just a second. A couple other terms to be familiar with before moving forward. An isolated system is a system that is not influenced by any external forces. So something like friction could slow an object down, but if we're looking at an isolated system, we're going to not consider any of those external forces that might play a factor. The other term that's going to be useful and going to keep popping up is center of mass. It's a useful concept for systems. It represents the average weighted position of all the objects within a system. So there aren't going to be any questions that are like, please calculate the center of mass of multiple objects. The only types of questions you're really going to see is if I screw around with this variable or this object, what happens to the center of mass? What changes? But we'll cover some examples like that in class. Another thing to be familiar with is the concept of mass and weight. So mass and weight, or the force of gravity, measure two very different things. Mass measures how much stuff an object is made up of, and it's measured in kilograms. Whereas weight measures the amount of force pulling down on an object and is measured in newtons. And so a simple equation is going to relate those two, and that is force of gravity is equal to mass times gravity. Gravity, of course, being 9.8 meters per second squared. Whereas m is mass, and force of gravity can also be considered weight. So let's break down what a force is. A force is a vector quantity that describes the interaction between objects or systems. Only an object external to the system can cause a change to that system. So an object can't really exert a force on itself. And there are two types. We're going to break down all the different types of forces, but we can categorize them in one of two different buckets. The first is a contact force, which is exerted due to direct contact between the two interacting objects. The other type of force is a field force that can be exerted over a distance. The only one that we're really going to talk about in this class is the force of gravity. Other ones exist like magnetic field force or electrical field force, but we're not going to cover those in this class. Okay, here are the 6 big types of forces. Let's take a couple minutes and break down each one. So first, the normal force, we'll also sometimes see it referred to as apparent weight. It is symbolized by capital F sub n in our equations. And anytime an object is resting on a surface, it's going to experience a normal force. It's sometimes referred to also as a support force. So anytime a surface is supporting an object, it's going to have a normal force. And it is always directed perpendicular to the surface. The next type of force that we're going to talk about is the gravitational force, also referred to as weight. So we'll see it come up as Fg, or sometimes just capital W for weight. It is present when, always, when we're talking about something on Earth, it's going to experience a force of gravity, or dealing with orbits. We're going to see force of gravity come up. And it's always directed straight down towards the center of mass of the planet. Next is the tension force, symbolized by capital F, subscript capital T. And that is present when an object is attached to a rope or a string. And it always follows the rope. Next is a friction force, capital F subscript little f, and it is present when two surfaces are sliding or trying to slide past each other. And it's always directed parallel to the surface and opposite motion, or attempted motion. All right, next we have an applied force, also could be referred to as like a push force. We'll symbolize that with a capital F sub A, and it's present when an object is applying a force directly on another object. And it's always going to be in the direction of attempted motion. And finally, our drag force, also known as air resistance, we'll symbolize it by capital F sub air. It is also a frictional force, right? And this time it's a frictional force on an object traveling through a fluid. That could be water, it could be air, but because it is a frictional force, it is also directed opposite motion. All right, there was a lot going on this slide, but yes, these are all the different types of forces that are going to pop up during our study on forces. Let's talk about net force. So the net force acting on a system is the sum of all the forces acting on that system. If there is an overall net force in one direction, the system will accelerate in that direction. But keep in mind, This does not necessarily mean the object is going to move in that direction, right? So if I, for instance, have one force of, we'll say, 7 newtons to the left and an object or in a force of 10 newtons to the right, the overall force, the overall net force is going to be 3 newtons in that direction, right? But that doesn't necessarily mean the object is moving in that direction. If, for instance, the 10 newtons was a frictional force and the 7 newtons was an applied force, right? The object could be moving in this direction, but slowing down, right? So we don't really know which way the object is moving just by knowing the direction of the net force. We just know which direction it's accelerating. If the net force is 0, meaning all the forces in the horizontal and the vertical completely balance, the object does not accelerate and will remain either at rest or moving at a constant velocity. So the best way to figure out what the net force is or the best way to visualize it at least, is by drawing a free body diagram. A free body diagram is a drawing that shows all the forces acting on an object. And they can help with trying to solve problems involving multiple forces. When making a force diagram, you'll replace the object with a dot, representing its center of mass, and each force acting on the object is represented with an arrow. The arrow's base must touch the dot, and the length of the arrow must relate to the strength of the force. So let's do a couple examples of that. A rightward force is applied to a book in order to move it across the desk at a constant velocity. Consider frictional forces. Well, if I look back at all the forces that I know I'll need to use this year, force of gravity is always present and it's always directed straight down. If the object is resting on a flat surface, right, it's going to have a normal force or support force directed perpendicular to it. Because it's not accelerating up or down, I know that these arrows have to be the same length. Now let's look in the horizontal. A rightward force is applied to the book, okay? But because it's moving at a constant velocity, I know that the frictional force has to be the same magnitude, but in the opposite direction. Now you'll notice that my horizontal arrows are not the same length as my vertical arrows. Doesn't matter. It's just these two arrows have to be equal and opposite, and these two arrows have to be equal and opposite if the object is at rest or moving at a constant velocity. Let's try another one. A sled is pulled by a rope at a 45-degree angle to the horizontal, to the right with little resistance, giving it a rightward acceleration. So let's say we have force of gravity always exists and always acts straight down, resting on a flat surface, so I know that normal force is also present. And then it looks like I have a tension force at a 45-degree angle to the horizontal. And it does say with little resistance, so I can assume friction is negligible or too small to worry about. And those forces do appear to be unbalanced, which causes an acceleration. So unbalanced forces cause an acceleration. A skydiver opens his parachute and experiences a huge deceleration. Well, I know force of gravity, it's always acting straight down. And if he's opening his parachute and accelerates, that means there's going to be some air resistance that is in the direction opposite motion. So if he's falling down, air resistance is directed up. And that arrow must be longer because he is decelerating. Lastly, a hockey puck is sliding along a frictionless sheet of ice at a constant velocity. If it's at a constant velocity, I know all forces have to be equal and opposite. I know that force of gravity is acting straight down, normal force perpendicular to the surface. Now, if it's moving, that's great, but remember, applied force is a contact force. So a contact force object has to be in direct contact, in this case, with the stick. So once that puck leaves the stick, it's no longer exerting a force on the hockey puck. So even though it's moving forward, this would be the appropriate force diagram for that situation. And finally, this diagram shows the direction and magnitude of the forces exerted on a puck on a horizontal surface. Notice this is the top view of a puck. What is the magnitude of the net force? Well, let's look at the forces acting in the horizontal, right? I have 7 newtons to the left, 3 newtons to the right, so the overall net force in the horizontal will be 4 newtons to the left. If I look at the vertical, 2 newtons up, 5 newtons down, so it would be an overall net force of 3 newtons in the direction of the larger force. So that means the net force would then be that. And if I want the magnitude of it, I'm just going to use a little Pythagorean theorem. 4 squared plus 3 squared gives me that hypotenuse. Force is then equal to 5 newtons. So in which direction is it accelerating? It always accelerates in the direction of the net force. And lastly, which direction is it moving? Well, like I mentioned earlier, it's impossible to know which direction it's actually moving unless you know the types of forces. So we are unable to determine without knowing the types of forces present. So that will do it for some introduction to forces. Bring any questions you have to the next class. Thanks for watching.